Today's review lecturer is Larus Thorlacius from the University of Iceland, and Larus will be talking about black hole informatics. So,
thank you. So, I'm going to give an overview or a summary of the black hole information problem. And so I'll do that. First, I will just do some very, elementary, remind you of a few elementary facts about black holes, classical black holes and semiclassical black holes. And then I will go through two ways of formulating the information problem. Then I will discuss briefly the various proposals that have been made, and there are many proposals for its resolution and sort of for what the physics is that's going on. And then sort of in the second half of the talk, I will inflict on you some of my own work on how, how I think this all works. And that'll be in a few parts. The first part will be recent work with David Lowe on trying to address this story in a context where we have some control via ADS-CFT. So I'll talk about the formation and evaporation of small ADS black holes. We will then, if time permits, I will also talk a little bit about recent work on, well, it's less recent, but on some aspects of the semi-classical physics of black holes that seems to be working better than you might actually expect. So that involves using semi-classical methods to compute the page curve of a black hole, evaporating black hole. And in a context, it's in a two-dimensional toy model where you can really do things analytically. And so that, I think, is a simplified context, and it actually works remarkably well. And as far as, and it's still, so the page curve can be computed in a semi-classical setting, but it will turn out, I don't think we have a very clear notion of why it's working. But, and then at the very end, if I have time, I will also run very briefly through another calculation in the same toy model, where one sees that the semi-classical geometry seems to know something about another fine-grained quantity. So the page curve has to do with entanglement entropy. There's another even more fine-grained quantity, which is the holographic quantum complexity, which one can compute using the semi-classical geometry and gets remarkably, well, basically spot on what you would expect from if this really is a dual description of quantum complexity in the dual quantum system. But let's before we start, I'm going to show you a few quotes. First one, appropriately, is from the paper that got all of this started. It's the original one, paper by Stephen Hawking on particle creation by black holes. Of course, the information problem he proposed somewhat later, but of course, this was the prerequisite. So I would say this is maybe a characteristically understated, it's a British understatement here. That, so there's been a lot of work in the last 15 years, and this is in 75. It would be fair to say that we don't yet have a fully satisfactory and consistent quantum theory of gravity. And now, 50 years later, I think it's still the case. Maybe another interesting thing here is if we look at, so this paper has almost 11,000 citations. And you can see that the interest in this problem seems to have been, so there was already some to start with, but it really took off here kind of around, in the early 90s. And it seems to be, growing at a rather rapid rate. Okay, so this was Hawking's attitude. For a different attitude, let's go across the pond. And this is like the final words of a very famous paper where they proposed the heterotic string. And I think it is fair to say that this claim has not aged quite as well as the one from Hawking. And then my favorite one a little bit later. That's from Sidney Coleman. He was doing Euclidean quantum gravity, and I'll let you read through it yourselves. And but I think this is something that we should all have in mind when we are working on problems involving quantum gravity. Okay, so black hole information problem. Let's first just do a very rough heuristic sketch of what that's about. Roughly speaking, we can put it this way. We imagine that we have matter that we arrange somehow to be in a pure quantum state. This is asymptotically flat space-time, and it's dispersed. So early on, there's very weak back reaction on the geometry. But then this matter undergoes gravitational collapse. It forms a black hole. And this is, of course, a process that we know happens. Black holes exist in nature. And they're also an inevitable consequence of the field equations of general relativity. And property of black holes, at least in 3+1 dimensions, is that very quickly after the black hole forms, takes time of order, what's often referred to as the light crossing time. That's time that it takes light to cross a distance, which is the Schwarzschild radius of the black hole. Within a few light crossing times, the black hole settles down to a sort of quasi-stationary setup. Let's imagine that there's no angular momentum here, and or even so. So there are these uniqueness theorems in four-dimensional gravity that tell, the O'Hare theorems, that tell us that we will have very little information that we can access about what went into forming the black hole, within a very short time from its formation. Now, this is not a problem of itself, because we can always just postulate that whatever information about the quantum state that we started with is residing, we can still attribute it to the black hole. We just have to say that we can't have access to it. The only thing we have access to a black hole is its energy, and it's basically charges that couple to long-range fields. So if it has an electric charge or angular momentum, that we can access, but very little else. But the information paradox comes about because Hawking's famous effect, the black hole doesn't just sit there, it gradually emits radiation. And in Hawking's semiclassical computation, that radiation is thermal. So it emits thermal radiation. If we allow ourselves to assume for the time being that the black hole will simply, the thing is, we have Hawking's computation, it applies as long as the black hole is macroscopic. It has to be large compared to the Planck scale. There basically are not allowed to be any large curvatures outside the black hole. This, of course, will break down at the very end when the black hole gets very small. So we perhaps don't have calculation of control over the end point of the evaporation, but up until that point, if we trust Hawking's computation, we will have emitted out a lot of radiation. So there will be sort of an outgoing train of radiation going in all directions. And if the black hole evaporates completely, that's all we're going to have at the end of the day. And then we would have an outgoing state that consists of thermal radiation. Of course, depending on how early in the process, the temperature is not constant for a four-dimensional black hole, but it's still a very good approximation. Thermal radiation, in particular, the important fact is whether it's exactly thermal, is not whether it's exactly has a thermal spectrum, but rather that it is in a mixed quantum state. We can't really tell from this radiation, what was the initial quantum state. And this is where the paradox comes in, because this is not supposed to happen in a quantum mechanical system. Quantum mechanical system is supposed to evolve in a unitary fashion. And if you have a pure state initially, then you should have a pure state at the end. And this seems to be a system. So when we include gravitational effects, Hawking argued, we will have to give up this notion of unitarity in time evolution. Okay, so that was backtrack though a little bit and remind ourselves of a few facts about black holes. And one thing that we will see in a minute is that this evaporation process is slow if you have a large black hole. And so we can, for a lot of calculations that we want to do, we can assume that at any given time, the space-time is going to be approximated really well by a static Schwarzschild black hole. And then it's almost an adiabatic, at least for a long time in the history of the black hole, would be an adiabatic evolution on the set of Schwarzschild geometries where we're losing mass. And there are two things to note about, so this is the Schwarzschild black hole in Schwarzschild coordinates. It has two apparent singularities. One of them is a true curvature singularity. That's the one at r equal to 0. There is a coordinate singularity at r equal to 2m. And if we compute an invariant, geometric invariant, like this Kretschmann invariant here, this is its value anywhere in this geometry. And in particular, if you look at what does it do, of course, it blows up at the origin, as it, that's where you have the singularity. But it actually goes like an inverse power of the black hole mass. So depending, if you have a very large black hole, the horizon, and actually everywhere outside the horizon, is very close to being flat. And this is important. This is why you would expect, if you start with a large black hole, that the usual notions of effective field theory, there are no large curvature invariants anywhere in the region where you're doing your computation. Of course, this will break down if you have to talk about the region that's close to the singularity. And of course, it will also break down once the black hole mass gets to be very small. That is, at the end point of the black hole, we can anticipate that we will not be able to trust our effective description. Okay. Let me also just to, I'm not going to go through the details here, but one usually does extends this space-time by sort of through the coordinate singularity. You do that by going to so-called Kruskal coordinates. And then one step further, you can contract or compactify this diagram here, and then you have basically the global space-time ADS. The part that was covered by our coordinate system before is just this quadrant here. This is outside the black hole, this is inside. But in the static solution, you have the second asymptotic region. And maybe the main point here is, the 2 points I wanted to make is that when we draw these diagrams, of course, at every point in the diagram, there is a two-sphere that comes along for the ride. And second point is that these are actually quantitative pictures. This is not just a way, a nice, you can draw things, but it actually, you can read off from this diagram things that you can refer back to the actual solution that you're working. So it's not just, and these things are a little bit tricky. You have to worry about, so what's faithfully depicted here is causal relationships. That is, if you have radial null rays, they actually travel along 45-degree lines here, but physical distance can be quite deceptive here. So you can have points, for example, up in this corner that appear in the diagram to be quite close to each other, but they are arbitrarily far separated in the space-time. So they have to be, used with some care. All right. So this is for the global Schwarzschild space-time. Now, of course, we are interested in this problem. We want something that is not just static, but we actually want something that will evolve, because we need to have, so our initial state that I had in my previous slide should be defined on some Cauchy surface here, which will be a space-like surface here early on. This can be the diffuse matter that's then collapsing and becomes the black hole. But this is, you can, for at least, for example, if you take a spherical shell of matter, you can solve this analytically, and you can again have a quantitative picture of you can read off quantities from this diagram. But even when we don't have an analytic solution, the sort of global structure here is robust. So what's defined as the black hole region is anything that cannot emit radiation radially out to this is where observers would be at late time. They would be sitting on some time-like surface close to out here. Basically, black hole region reasonably is the region of space-time from which light cannot escape. It will basically, all points in here have all time-like and no future directed curves here. They will intersect the singularity. And the boundary of the black hole region is called the event horizon. And this is a global concept. You can't draw that until you have the full evolution of the system. Okay, so this is the classical picture of a black hole that forms, but we want to go beyond that. We want to actually study semiclassical black holes. So these are black holes that actually evaporate. They will. So let me spend just one slide on the Hawking effect. So Hawking's calculation is a semi-classical calculation in that he takes this background, which is the background of a black hole formed in collapse, and he does quantum field theory on this background. So this is what you usually mean by semi-classical. Now, he does not include the back reaction on the geometry due to whatever semi-classical effects that he sees in there. So that's something we want to talk about later on. And there's sort of a very heuristic way of understanding his result, which is that we're doing quantum field theory in curved spacetime. And in quantum field theory, in the vacuum, there are always particles that are being pair created and annihilated. And if this happens outside the black hole and sort of in the asymptotically flat region, we know what happens. They will not last very long. They will reconnect within time that's given by particles have energy E, then basically they will annihilate within a very short time that basically depends on the energy of the particle. Okay. Now, if this virtual pair is actually created across with one of the members on one side of the horizon and the other on the other, then it turns out that you can argue, and this is, I said, it's a heuristic argument, but then you find that the member of the pair that has positive energy can propagate on the outside. The one that has negative energy in this pair, because of the way the metric, the time is space-like inside the black hole region, you can basically, what you find is that the positive energy member of the pair can propagate out to infinity, and the negative one will hit the singularity. Now, the net effect of that is, of course, that the black hole has sent out a particle with positive energy, and it has absorbed a particle with negative energy, which means the black hole mass will get smaller. Now, this, of course, is not reflected in this diagram here, because, or in Hawking's computation, because he assumes a fixed background. But of course, over time, if this goes on long enough, you will find that there will be, there has to be a back reaction on the geometry. And the way you see that in Hawking's computation, now the actual computation that's in Hawking's paper is, of course, actually does not refer to anything like this. It's simply the simplest thing. You take a scalar field theory and you carry out sort of standard quantization, canonical quantization of the scalar field in this background. And you do that by solving the Klein-Gordon equation. You do a mode expansion. You then define your Fock vacuum by having the positive frequency modes annihilate your vacuum, and then you can build up your states using creation operators. This you can all do, let's say, on a Cauchy surface here in the far past, where things are pretty much flat, but weakly curved. You can also do it up here outside the black hole and far away at late times. But the problem is that the two vacua, there's a mismatch between them. If you're doing this in Minkowski space, one of the first things that you show when you're doing quantum field theory in curved spacetime is that you show that the vacuum is actually Poincare invariant. It doesn't matter which slice, how as you evolve the system along in time, your vacuum stays the same. And so the notion of a particle and an antiparticle, they stay the same. This is not true anymore when you're in curved space-time. And the effect that Hawking saw actually can be traced to the fact that the modes defined with respect to Schwarzschild time at early times and the modes that you defined, positive frequency, negative frequency, at late times, they're not the same. You can compute overlaps between them. And that you do by taking, mode solution here, and you basically evolve them backwards. And there are technical issues in this computation. For example, when you evolve them back, it turns out that most of the effect comes from the region, comes from modes when you trace them backwards here that are extremely close to they're in fact exponentially close to this horizon curve. This is simply a fact that you see when you're doing the computation. And then you reflect them off the origin here, and you go out here. And then you notice that when you want to compute, and then to compute the Bogoliubov coefficients to figure out the relation between the mode expansions, you have to do an overlap integral between the mode that you've extended backwards and out here, and then with the regular modes out here. But you see that the ones that you're working your way backwards from, they only have support on, below here. There's no support up here. And this is, when you push this through and you actually do the integrals, you find that you will get that they are Bogoliubov coefficient correspond to a thermal, basically give you a thermal. First of all, what you find is that if you start with, if your state starts out here and it's in the vacuum, that is no longer the vacuum up here. And that you will find that if in a state where there's the vacuum down here, you will find that there's outgoing radiation out here. This is basically how it obtained this effect. But and then due to this rather sharp boundary that you have here, when you're extending your way backward, you find that it's actually precisely thermal in this case, in Hawking's computation. Now there are subtleties here. Like I said, that you are getting most of your effect from extremely close to the horizon. In fact, when you do this tracing back of your mode, there is a red shift or a blue shift, if you like. The modes that are coming out very late times, they look as if they are emerging from extremely close to the horizon here. And they have been exponentially redshifted on the way out, which means they started out as being highly transplanckian modes down here. Hawking actually uses that to good effect. He says these modes are so high energy, it doesn't matter that you have a whole star here that they're going through. He just uses the geometry, uses geometric optics. And so you can question these things. And of course, they were questioned back in the 70s and 80s. It turns out there are other ways to see the same effect, but this is maybe a first example of something that will be a bit of a recurring theme here, which is that you can make arguments using, and do computations in different ways. Physics appears to be rather different. In this way, there appears to be the key role played by modes that are extremely high energy. Now, there are other ways to do this computation where there are no such modes anywhere. And the effect has to do with apparently very different physics. But at the end of the day, of course, what we the important thing is that these different methods, they all agree that there will be thermal radiation coming out here. So, and we're going to see this, yes. Yeah, okay, sure. There are great body factors indeed, because of this is when I ignore backscattering in the so there is curvature here. Yes, it is close to thermal, but there are backscattering, absolutely. They will not have much to do with have much impact on the story that I want to tell, but thank you. Yes, absolutely. It's not exactly. Okay, so So we want to think about the background. So energy cost. Okay, one more thing about if you actually do this computation, you can get that there is a thermal radiation coming out. Now, of course, as you go closer and closer to the horizon, basically time, the black hole just stays there forever and it's radiating. So clearly there will be, if you compute the total amount of energy that's emitted, it'll diverge. And that's because we have ignored this back reaction. So that is not consistent. So you want to get to a picture where you avoid that. And you can estimate kind of how this back reaction has to happen. You can calculate the rate. First of all, the temperature that you get is inverse in the black hole mass and in 3+1 dimensions. Now, okay, some of the things I talk about later will be in different numbers of dimensions, but for sort of simplicity, I have all my formulas here just, for the most part, they're in 3+1 dimensions. Okay. If you can now use the Stefan-Boltzmann law for a source that has the area of the black hole at this temperature, you can estimate what the energy flux is, and you can sort of get a differential equation that tells you at what rate is the black hole losing mass. And you can integrate that, and it tells you that the lifetime of the black hole will go like the mass cubed. And this will be important in the later part of the talk. And for a solar mass black hole, or the kind of astrophysical black holes that we're seeing evidence for out there, this is an extremely long time. Compared to the age of the universe, where a solar mass black hole would have barely started to evaporate. But we're not going to worry about that, of course, because we're thinking here about some sort of the formal structure of our theory. Another important piece of information that comes out of this is that we learned from Bekenstein that in order to preserve the second law of thermodynamics, we had to attribute an entropy to the black hole, and that entropy would be proportional to the area. And then once Hawking did his computation, he could actually put a number in front, and that it was the quarter of the area in Planck units that gave you the black hole entropy. And we could compute this for a solar mass black hole, and we find that it's rather a large number. And an interesting observation that was made by Bekenstein is that if you take the thermal entropy of the sun, which would then conceivably go and form a black hole, its thermal entropy is tiny compared to the actual entropy of the black hole. So if we want to have a statistical mechanical or a quantum mechanical understanding of the black hole entropy, it cannot be that it's the motions of the particles that are forming, if you have a collapsing body, it has to be something else. And this will be important in the second part of we will basically, there are arguments made by Zurek and Mukhanov to sort of the nature of the states that form possible initial states to form a black hole. You can actually enumerate them and get at least parametrically this entropy right. Okay. Now, what about the geometry? Well, the geometry has to respond. Black hole has to get smaller. And this is a hard problem in 3+1 dimensional. It hasn't been solved. You can, of course, do the kind of sort of just make this assumption of that you have an adiabatic evolution, and that's probably going to get it right. But actually solving the Einstein equations with semiclassical corrections has not been done. In fact, even just getting a self-consistent set of equations that incorporates this has proven to be quite hard, and that has to do with both the non-locality of the quantum effective action, but also its subtleties in how you have to regulate the stress tensor, the energy momentum tensor that comes on the right-hand side of your Einstein equations. Now, this has been done in 2 dimensions. And when particularly in a very simple model by Kylan, Giddings, Harvey, and Strominger back in '92, they found a model which you could basically, it's 2-dimensional dilaton gravity, which doesn't contain any local dynamics, but you can add local dynamics by adding matter, and they chose very cleverly just conformal, a set of some number of conformal conformally coupled scalar fields, basically free fields in 2 dimensions. And by taking the number of those fields large, they could kind of ignore subtleties that had to do with how you actually quantize two-dimensional gravity. And the key thing in 2 dimensions, when your matter is conformal, you can get a long way just by knowing that it has, knowing about the conformal anomaly. And by integrating the conformal anomaly, this is done by Polyakov, you get a set of dynamical equations that you can actually then just proceed to solve. And I will show you this model later on if I get there. In fact, I will show you a variant on it that we shortly afterwards came up with Jorge Russo and Lenny Susskind, where we just added a simple term that was allowed by the symmetries of the model, and it really simplified the semiclassical analysis. Actually allowed us to compute in this RST model, as it's called. You can take an arbitrary incoming flux of these matter fields. You can compute analytically the back reaction, so the metric that it leads to, and you find that black holes form, and they do evaporate. And you can study that in quite a lot of detail. Now, the analog problem in 4 dimensions, as I said, has proven hard. In recent work with David Lowe, we've proposed a set of equations that we believe will capture this. They're hard to, first of all, they're non-local, they're highly nonlinear, and they are also, what happens to in higher derivatives is, higher dimensions is that they also become higher derivatives. So they're fourth order in time derivatives. And this all needs some care in how you deal with. But we're working on some simple, and we want to test these equations. The obvious thing is to start thinking about spherically symmetric collapse. But those equations will only have a shot at solving numerically, I think, and we're sort of working on that. But the 2D models can give us some intuition about what the Penrose diagram is going to look like. And it's certainly our expectation that once we solve this problem, or someone does, we will get a picture that looks very much like this. So again, we form a black hole, it evaporates by sending out Hawking radiation. Then the size of the black hole shrinks, and you can study this explicitly in these 2D models. And to the point that it actually, there's an endpoint in the model. That's actually where the semiclassical picture breaks down. There's a little bit of an embarrassment there. There's you have to do an adjustment, kind of patch together onto a flat space-time, in the future here. But that patching involves what in these models amounts to basically 1 Planck mass or Planck energy worth. So, we didn't expect our semiclassical description to work here anyway, and it's actually kind of a minimal failure there. And so and in any case, and this is true always in these stories, most of the Hawking radiation will get emitted before you get into this region where you maybe shouldn't believe what you have. All right, so these are semiclassical black holes, and now we can start. No, this comes from the regularized stress tensor on the right-hand side. You use geodesic point splitting. This is a venerable old method from DeWitt. And the problems, and you do your point splitting, you subtract off what's called the Hadamard elementary solution, which basically you're subtracting off the divergent part. Let's say you're doing scalar. You do a scalar field. Your stress tensor is sort of a composite operator from involving 2-point functions and derivatives of them. Once you've done all your subtractions, and the problem is that has stymied people over the years is that when your subtracted green function doesn't satisfy the field equation, the Klein-Gordon equation. And so our way around that is we actually work with unsubtracted ones. We evolve those using Schwinger-Dyson equations. But that means we actually have to keep track of both. So they're very non-local because we have basically a unsubtracted 2-point functions of x and x prime, two events. So at the end of the day, and this fourth order in time derivative, this has been known for a long time. This has they have been Wald, I think, that worked that out in the 80s. So, but no, it does not come from the left-hand side. But of course, what you do, you take, your stress tensor, and you insert that into some, at least is our strategy. We're going to insert that into some numerical GR solver. But you do have to, tread carefully with your. But the way we plan to handle it is to do a perturbative expansion, a semiclassical perturbative expansion. Because of course the worry is that if you have higher time derivatives, you will have also spurious solutions. So you need to make sure that you're not picking those up in your numerics. So, well, we haven't solved it yet, but we have some ideas how to get at that. All right.
More like that. More only information has come out already.
No, this has nothing to do with information. This is just the semiclassical evolution. It is this was just in order to, we can solve the equations. And what we found was that if you look at what the solution looks like here, we could patch it onto a flat empty space-time in a, after the black hole, but at the price of an outgoing shock wave.
That's a point.
Right.
That's
right.
What I mean. That the state outside is high in time.
No, I mean this model you lose information, semiclassically, and if the information is recovered, then clearly,
Then it's
sure. Then look, and this actually in our original paper on black hole complementarity, we studied this model as a case study, and what we found is that we could define a stretched horizon. I'm getting ahead of myself a little bit here, and in fact, we had boundary conditions that were non-local in the matter fields and kind of mysterious from that point of view. But what they did exactly was to have that stretched horizon nicely emit thermal radiation, and yes, nothing. Well, we didn't work it out, but our assumption was that we would not have to do any patching. Now, all right. So it is getting quite unlikely that I'll get to the complexity at the end, but that's okay. I will just stop when the time is up. All right. So let's formulate the paradox. Now I'm going to use two formulations. One is kind of a time-honored, fairly standard one that has been subjected to a lot of criticism, I think justly so. And then I'll have a second one, which I think is at least does not suffer from those problems. Now but I think what that tells me and is telling us, I believe, is that again there are different ways to formulate problems, and the end result will be the same, but perhaps so I think the important thing is that if we have a formulation of the paradox that does not involve technical issues that are out of our control, then maybe we should have more faith. But let's just run through this one. So first of all, we're going to assume quantum mechanical unitarity. So we're going to assume that we have a system that starts out in an initial state, and this will be a pure state that describes the matter and the gravitational field in some effective field theory at early times. And I think that's not controversial, that people expect to be able to do that. describe everyday physics in some effective field theory, in fact. Now, if the evolution is unitary, then there will be a unitary S matrix that relates the final state and the initial state. And this means that we can express the initial states. If we have the final state, we have all the information we need to know what was the initial state. And this, of course, was the problem that we're going to run into, that we don't actually have that. All right. And we're going to make some assumptions. And I think it's important to note that this information paradox is always a problem of effective field theory. It's actually a kind of a subtle breakdown of effective field theory. Now, of course, the effective field theory paradigm has been extraordinarily successful. It is, of course, underlies our particle physics. And well, general relativity is an effective field theory. Einstein looked at the leading terms and sort of he ignored higher order terms in curvature because it was clear that these were going to be tiny compared to, and on the length scales that he was going to do tests of his theory. So we're going to assume that we can approach this problem, that we use an effective field theory. But we're going to only assume that we can use it in regions where the curvature is weak. That's far from the black hole singularity. And we're actually not going to have to worry so much about exact explicit form. Of course, if we want to do quantitative computations, then we need to know what the explicit form is. And then the approach is that you start by constructing a convenient set of Cauchy surfaces. So our space-time is going to have a tenorous diagram that looks something like this. And we're going to now foliate this space-time with some Cauchy surfaces that satisfy this condition, that they avoid basically this region here. But there's a further condition that they have to satisfy, which is that they're not allowed to have strong extrinsic curvature either. Because you would expect that if you have kinks in your Cauchy surfaces, those are or caustics or something like that, those can also give rise to things that would would lead to a breakdown of your effective field theory. And we're going to assume that in this effective field theory, we have a Hamiltonian that will generate a unitary evolution from one Cauchy surface to the next. And then the next step is to start doing this. And now, of course, you have to ask, can you actually find a set of Cauchy surfaces that satisfy these conditions, in particular that avoid the singularity long enough? And this was sort of sketched by Robert Wald back in '93, and then we worked out a kind of a detailed sort of construction of these surfaces. These are called nice time slices. They're nice because they satisfy these properties. It turns out they're locally nice, but what we will find is that globally maybe they're not so nice. And this has then been elaborated on by Giddings and others probably. Okay, so now we have our thing, and it's going to run through this just quickly now. Here's your initial state. It's going to evolve in a unitary fashion to a state that's on a nice slice that is partially inside the black hole region. And by assumption, there will be a unitary relation then between the state on this slice and the state on this slice. Now, at the same time, we are going to insist, if the whole thing is unitary overall, that there be a unitary S matrix that takes us from initial to final here. And this is, of course, going to be a problem because in our local effective field theory, we would be able to take the external part of this guy, the state, so the state defined on the external part of this Cauchy, so evolve that using our effective field theory Hamiltonian. So this state out here should have a unitary relationship to this one here and to the only part of this one here. And if we assume that that we have a tensor product Hilbert space, which of course is an assumption that is questionable, then this, of course, we see that this cannot be the case because there will be entanglement of whatever state you started with here. There is entanglement, if you like, in this part of the state here with things that are on the inside here. And that means that there will be entanglement here also in here. So therefore, the final state up here will in fact be a mixed state. All right. Yep.
The assumption for factorization.
Yep.
Is quite debated.
Absolutely.
What is your argument?
It's version 2. I'm going to do a second one which doesn't do that at all. But yeah, let's say it mainly, this is a simple argument. This is also a fairly standard argument, but I also wanted to be, to bring up that there are issues here with this. And in particular, and there are, a lot of discussion that, in a relativistic quantum field theory, you can't take a trace over your Hilbert space. And so, yeah, this is, if this was the only way to make this argument, I would worry. Okay. But I think what is not controversial is that when you have, if you have a local effective field theory that's evolving in this way, there will be entanglement across the horizon that you can make, do in fairly straightforward way. This is argued nicely in a paper by Wald and Unruh, where they're arguing for information loss, where basically they think about a two-point function. So entanglement means that if you have a two-point function of some operators, the expectation value can not be the product just of the expectation values of the separate operators. Okay, that's only true if they're in a product state. Okay, and then if you just think about a two-point function of scalar operators, with one of the points on one side of the horizon, the other one on the other, you let them approach the horizon from either side, there will be a divergence that you need to deal with. That I would.
There's no local. And so how do you define one function? So you have to.
This is yeah. So that's a second thing which one should worry about here. But I can make this argument though, for example, in the 2D, I can go through exactly the same story in the 2D models, where I know how to solve the constraints. In fact, they're already solved. And there you will run into this issue. Okay. And sure, this is another, and thanks for pointing it out, this is another technical issue here. Because of the second argument I have, I don't think that's going to be without being able to say for absolutely sure, but I think, so let's just go to the second one. Yeah, so we're gonna just analyze a certain Gedanken experiment. And it's a Gedanken experiment we can imagine being carried out by some low energy observers. And I think we would say even though you have gravitational dressing, you should be able to do use Stern-Gerlach apparatus to measure spin. So that's more or less what we're going to do. So these are it's a variant on a type of experiment that Lenny Susskind and I proposed back in '93, and we jazzed it up a little bit in this paper with David Lowe. And so it's a following. The starting point is you form a singlet, and you think about taking one member of the pair into the black hole, and the other one you take far away. And the spin 2 is actually kept by Charlie here. Alice goes in, so it's Alice, Bob, and Charlie that you need here for this. Alice and Bob, the story doesn't end well for them, but Charlie has it all. He keeps his spin out here, and then the setup is that at an agreed upon time on these slices here, Charlie does a measurement, but before he does a measurement, he flips a coin. So it's 50-50 chance whether he measures the X or the Z component of the spin, right? And of course, there should be no way for these two to know that because this is a space-like surface. So if they can find out what he did, that means we will have a causal propagation here. And now, normally EPR correlations don't do this. And the reason this will lead to a problem is because we're making an assumption that the information about the state of this spin is actually contained in the information that can be read from the Hawking resolution. This is basically a duplication of the quantum information of the spin. Now, this, of course, is not something that quantum mechanics is happy with. And the way we see that here explicitly, for example, is that we then instruct Alice to take the other spin in here, and she measures it along Z. And she does so as quickly as she can when she's inside the horizon and broadcasts the result. Of course, Bob and Charlie will not know what she got unless Bob goes into the black hole. So that is the last part of the thing. Bob basically keeps track of the Hawking radiation that comes out, and never mind how he does that, or you know, so engineering aspects of this are probably quite challenging. Furthermore, it's not enough to just have one pair of spins. Of course, you need a whole. You know, you want to do to measure the state of a spin, you would have to have identically prepared pairs, and so you want to do statistics on this. But that you can do. You can label the members of you know. Let's say you have 100,000 pairs, and Charlie just does his measurements on that. So he flips his coin, and then he either measures all of them, the X component, or all of them, Z component. Alice always measures the Z component. Bob actually, by observing the Hawking ratio, you know, can also measure the Z component. Right? And this is the assumption that all of this can be done on nice slices where we do local effective field theory. These are independent measurements by Alice and Bob, where they're actually doing the measurement of the spins. So now Bob enters the black hole, having done his measurements. And if his measurements on the spins don't always agree with what Alice tells him, then he knows that Charlie measured along the x-axis. So there's some probability for Bob to discover that what Charlie did. That means we violated causality. Okay, so this is one way to see that. And you notice in this form, we were always away from the strong curvature region. We didn't do any traces. We just did measurements that we can imagine low energy observers to make. And so this leads to a contradiction, obviously. So what are the resolutions? Well, people have, of course, come up with. Hawking said, well, and this was implied in his original, when he formulated the paradox first, he said, well, obviously, you simply can't, Bob can't do any measurement. There's no information coming out in the Hawking radiation. So that is a proposal. And that's basically that once you take gravitational effects into account, there will be non-unitary evolution. So we start from an initial state in a initial pure state. We form our black hole, the black hole evaporates, and then we end up with what is not a pure state, and we just have to deal with it. And Hawking, of course, will give him that, but he tried to deal with it. He formulated a generalization of quantum mechanics, where instead of evolving Hamiltonian evolution of states, it was the basic variables were density matrices. And instead of having an S matrix that took you from an initial state to a final state, he had a superscattering matrix, which took you from an initial density matrix to a final density matrix, and in such a way that you could, in fact, allow for processes where a pure sort of the trace of rho squared would actually change on your, assuming that you could actually trace your density matrix. But anyway, so that was a proposal in 82. And we'll come back to that in a minute. Now, there are other possibilities. Maybe the information doesn't come out in the radiation, but it actually just stays there. And the black hole doesn't completely evaporate. Remember, we don't have control over the endpoint of the evaporation. So black hole could conceivably just end up in a tiny nugget. Now, it's supposed to semiclassical physics is supposed to hold until you get close to the Planck scale. So these remnants, which is what they're called, should then be Planck scale. That was in this paper by Aharonov, Kasher, and Ustinov. There was an elaboration on that in a paper by Banks and Laughlin in the 90s. And we'll also come back to this in a minute. Why this? Now, so there are problems with both of these, both with the information loss and with the remnants. Very early on, Don Page had argued that the information simply had to come back out in the radiation, and that you would have to modify the gravitational physics in order to accommodate that. This was then seconded and amplified by Tuft, who in a series of papers attempted to compute an explicit S matrix for evaporation, but those papers were a little bit, well, I would say rather hard to follow what exactly he was doing. I remember when I was first getting started in this business, Lenny Susskind was introducing this problem to us, and he sort of mused that that Tuft had gotten the physics right, but that he had insisted on being obscure, and that our contribution, our task was to try to sort of demystify what was going on in that approach. And so that was this where we proposed this. It's called black hole complementarity, which I'll tell you about in a minute. And there were very similar ideas coming from Kim and the Villende brothers at the same time. Now there's of course, since then there have been other developments where you have sort of variations on this theme. Now, this information problem is, of course, a problem where you have black holes forming and evaporating. Now, if you're doing ADS-CFT, of course, it's the black holes that we have a handle on there are eternal black holes. They're black holes that are not going anywhere. And Juan Maldacena pointed out that there are properties that if you have a unitary theory, the very long time evolution of correlation functions in these backgrounds should have certain properties. And so I include this here as kind of part of this story and then there was the final state projection, which is basically where the information and the state that part of the state that was propagating inside black hole region, when it gets to the singularity, gets projected onto a sort of the information gets removed from it by a projection. That will, of course, take care of it. Then it will no longer be entangled with the outside. But exactly what is the physics of how this? I mean, this was by fiat, I would say, force of will, or I don't think we have a very good. We don't have a theory or a good understanding of how this goes about. So I will not have much to say about that. And then Giddings has been arguing that you can actually make small or parametrically small introduce interactions between the infalling matter and outgoing radiation, not very, very close to the, basically in this region of order the black hole size itself outside. And that would be enough to transfer information from infall now these will have to be non-local. So there is you cannot do this without violating locality, but Giddings tries to argue that you can do this in a way that can be quite mild, and doesn't lead to any major damage to your geometry. So I won't go much into that. You could say that black hole complementarity is an example of this. That is, the infalling observers are not really running into much drama, but on the other hand, the degree of non-locality in that picture is actually much greater. And I'll come to that in a minute. You're really, you are giving up locality in a major way. Now, of course, there are other proposals that have come, in particular the fuzzball proposal, which says that that these things are actually, once you understand the theory of quantum gravity, black holes are actually not singular. again, those are I will not have much to say about fuzzballs, but although in some later work by Mathur, he has argued that fuzzball will in fact evaporate. Fuzzball might have, interact with an infalling observer in such a way that perhaps this notion of black hole complementarity and the physics of falling into a fuzzball might not be distinguishable. I think that's, but again, Mathur might not agree. This is not original to him. This was done by Slava Mukhanov. Thank you for pointing it out. I had forgotten that from my list. Slava Mukhanov and Brandenberger had models where they actually put in to the way they implemented it, they put in constraints, maximal curvature constraints. And then what happens is that you will basically, instead of having a singularity, you get a wormhole into basically have a de Sitter region, if I remember correctly. And anyway, you will then have a way of getting rid of information into another. That, of course, means information loss for us who are sitting in this universe. So then you will need some sort of third quantization. And people tried this back in the late 80s. This was this paper that Coleman, I cited at the beginning, was on that. Again, details, without going into any details, the consensus at the end of that development was that, yes, you could imagine doing this, but that once you had, basically, if you integrated out the other, the other components of your multiverse, if you like, you would end up with a probability distribution for your couplings. And then you could say, okay, I will have that, but now I will just run my experiment again. And in the effective theory with these, the couplings have some value that is determined by the, I'm going to have information loss again. So it didn't really solve the problem, but it was, unless you can come up with a working theory of these multiverse evolution, that may well be possible. Okay, there's also this Sauter proposal, which is kind of our. Now, the suggestion there is that the information doesn't actually go into the black hole. It's kind of left, a trace of it is left. There are some issues with this, this is really a classical story that they have here. I don't think it has been worked out at finite G Newton. Now, of course, if G Newton is not finite, black hole doesn't evaporate. You don't have this problem in the first place. So there are issues there again, but very interesting development. And let me, before I go on, let me sort of set up this triangle here that what the information problem is telling us is there are these three very fundamental notions that we know and love. And we would like all of them to be true, but basically the conclusion is that you have to give up at least one of them. And and of course, information loss in Hawking's, you gave up unitarity. You assumed locality, and Hawking, of course, was also assuming the equivalence principle that the horizon was not a very particularly large black hole. The horizon was weakly curved. Now, if you're thinking about fuzzballs or black hole complementarity, then it's locality that you're giving up. And that's, we claim, is the lesser evil, if you like. Right. Well, I'm using it in the sense that a local effective field theory will fail.
That's probably the strongest form of locality.
Right.
Whether we need that or not.
It may be that you can resolve all these issues if you manage to develop a theory that has that. But I'm thinking about theories that only have local terms in an effective Hamiltonian. Yes, right. Well, no, I'm saying that if I assume that I have a local effective Hamiltonian, I will still run into trouble. Okay. Okay. And then the remnants are, then you, of course, are giving up the equivalence principle, small remnants. Now, of course, this is large remnants. On the other hand, this is a proposal from Steve Giddings that the black hole actually forms and then just stops evaporating for some, non-semiclassical reason. The weakness of that is, of course, we really don't know what that physics should be. And therefore, they simply don't evaporate. And then if you don't run into this problem, then the black hole just holds on to its information and stays around. That I would say is then you're giving up the equivalence principle. And the firewall proposal is kind of that type. It says that you're certainly giving up the equivalence principle if if observers will simply burn up upon entering a black hole. But we'll come maybe back to that in a little bit. So these are some of the suggested resolutions. I've been reminded of a couple more as we go through here. So let's look at a couple of them. Now, I should give you a disclaimer here. Obviously, I am not I'm I don't know, honest broker or whatever you want to call it here. I have an opinion. And the opinion, of course, was given away by the title of my talk, right? I call it black hole informatics. And if you look up in the dictionary, what is informatics? Well, it is the science of processing data for storage and retrieval. And the claim is that black holes will store information. And then, well, if you're advanced enough and can do, subtle observations on Hawking radiation for a whole, of course, ensemble of identically prepared black holes, then you should be able to read off the information, the initial data. Well, I'll admit to laziness. I simply, it's the one that's on my Mac. All right. So, all right. Information loss. So this was Hawking's proposal that you could actually just try to do generalized quantum mechanics, as I mentioned earlier. Now, the problem with this is, was pointed out by several authors soon afterwards, is that they don't really prove that this cannot be done. What they do is they came up with a model where you realize this generalized quantum mechanics in terms of ordinary quantum theory coupled to sources. Okay, so this is basically you view the system that you and this is reasonable from if you think about where we're coming from. You basically have to think about an open quantum system, right? And then the claim was that these sources, in order to get the specifics of Hawking's generalized quantum mechanics, these had to be random sources with basically order 1 in Planck units. And so that meant that you could say that this theory kind of just, the phenomenology doesn't work, and that the state that you would expect to see would be a thermal state at the Planck temperature and not empty spacetime. Okay, now there are technical assumptions that go into this, which have been disputed, in particular by Unruh and Wald. So I would say the jury is out whether you can actually formulate a theory that is a fundamental quantum theory that actually incorporates information loss. It's not something that most people in the community are not really thinking of those lines, but I don't think we should write it offhand. I think it has been. Now, and that has been kind of the main point of these papers by Unruh and Wald. They haven't really offered us a theory of how it actually would work. They're simply pointing out that the arguments made here may not may not be as general as people have taken them to be. Okay, so that's something to keep in mind, that possibly information is lost, and I'm wrong. That's how about remnants? I'm more confident that there are no remnants. Now, why is that? Well, imagine that you have a stable remnant at the Planck scale. But you have to remember, black holes can start out at arbitrary size, and they can have arbitrarily large entropy. And you need to have a distinct remnant for every possible black hole state. So you need a lot of remnants. In fact, you need an infinite number of remnants. And infinite degeneracy of states is going to be a problem for you. Imagine any amplitude. Take a process, and you can think about a loop correction to that amplitude where you have a remnant going through a loop. Obviously, it's gravitationally coupled. It's going to be extremely weak contribution from a single remnant, but there's an infinite number of them. You have to sum over all of them. And so you run into basically any quantum amplitude that you want to compute will diverge. So there are real technical problems with this. Now, you can have, there's a loophole that Banks and O'Loughlin pointed out, were developed, and those were, again, based on intuition, came from two-dimensional models, which were kind of S-wave reductions of certain dilatonic black holes that had these very, very long throats. And then you could imagine having the information about the original black hole sort of be stored way down the throat. And then actually it would be hard to get at, and you might find that there's a further suppression in the contribution. And let's say the more information that's in the remnant, the harder it is to get at. Now, of course, at the end of the day, that probably then will be a theory that's effectively just has information loss. So again, you would then have to figure out how to get that to work. But I would say, in fairness, that it has not been proven that this cannot happen. I think maybe the sociology of it is that ADS-CFT came on the scene, D-branes and such, and we basically, at least in the string theory community, we think we know what the degrees of freedom are that the fundamental theory has, and they're not remnants. And that may be the strongest argument against them. Okay, now unitary black hole evolution, of course, is what I will focus on from here on. And this was pioneered by Page, and then sort of has been worked on. And now, of course, the list goes on. It's has many, many different proposals have come. Let me focus on the one that sort of our approach to this, which was we put forward a set of assumptions or postulates in this paper in '93. And there were 3 of them in particular. And then I'm gonna include this 4th one here. Now, first one is that we should think of a black hole as a quantum system with discrete energy levels and finite density of states. Okay? And in fact, that this density of states is characterized by the Bekenstein-Hawking entropy. So that tells you that there's a subspace of states that describe black holes of mass m, and that's going to have an e to the, will be dimension of that will be e to the s. Now, this, of course, is an extremely strong assumption. It's saying that your black hole and all that's in it is actually described by a finite dimensional quantum mechanical quantum system. All right. Now, these 2 assumptions are nowadays sometimes referred to as the central dogma of this business, and then this is, of course, just a statement of unitarity. So we just put that down as that was going to be an assumption here. And then there's the one that we could have a problem with, but I have a mild version of it here. I say after the black hole forms, the full system can be divided into subsystems. And the one subsystem, which I don't think should be very controversial, is if you have your Hawking radiation that's going out far away, it's just ripples in gravity and in gauge fields. And so that we can think of as being, in fact, if we're going to do effective field theory at all, we always think of being able to describe radiation and matter in some as a quantum system. And this, we will put some distance. Let's say we go a light year away from our black hole. And anything outside that is one system, and whatever is on the inside, black hole included, is the other system. Okay.
Weak gravity at zero gravity. And you are saying that weak gravity, you can approximate this as zero gravity.
I think what I want to say is that we do our experiments and we do physics in weak gravity. And for example, my second formulation of the problem did not require, zero gravity anywhere. So I want to think sort of operationally about measurements and observations that can be made. And there can be measurements and observations made on radiation going off to infinity, even if it hasn't gone all the way out. Right. That's
related to this. If you're making measurements, I understand the picture, but if you divide them into subsystems, is this consistent with gating different values? You're making a physical observation, you sort of break it by choice.
Yep.
So that's different from dividing into subsystems.
It is, right. And much of what I have to say doesn't really require this. Okay. Now this picture, for example, 1 and 2, if it's really true that you can, in some operational way, replace the black hole by a finite dimensional quantum system, then of course you can think about that as being, that's, that will be then a subsystem, if you like. Okay. And so if but the reason, of course, I wanted to include this for here is to be able to have a discussion about page curve, which I'd be saved by the clock, I think, so we won't actually get there. But let's say that, for the sake of argument, that I cannot do this. Okay. Well, that means we shouldn't really be very interested in page curves for black holes. Fair enough. Yet, not particularly, no, but because I think, although I will admit that I don't have a sharp technical definition of how I would describe my finite dimensional black hole system. If I've made that assumption, then then I should be able to, think about the entanglement of that system with the rest of the world, and imagine, then the page curve should have meaning. Okay. But now the reason I'm hesitant to buy into that is because I think possibly this is an indication that we have to take a further step now, which is that maybe we have to treat the entire system. So what I'm saying here is that the interior of a black hole in this way will be viewed as a geometry that emerges from some quantum mechanical degrees of freedom that we associate with the horizon. Or perhaps the whole world needs to be viewed as emerging, and that this field theoretic local description that we use is extremely useful, but at a fundamental level it does not apply. At which point I would then no longer say that then I would say I'm more allowed to think about dividing things into subsystems. And I guess my rationale for that is, black holes can be very large. There can be a very, very large geometry on this side that is being described in an emergent fashion. Holography, of course, says that all of ADS is emergent in some sense from, in fact, in a rather precise sense from the gauge theory. Okay. So anyway, having said that, if you have a
are related by one of them is what are the microchips for that problem? The second question is what's happening to a server on the server? That we made a lot of progress understanding microchips of the
absolutely.
having a silver state of finite dimension. That's a record for me. But still, it doesn't tell us what the.
Well, that was going to be the second half of the talk. I was going to tell you that now. Can we do it in 10 minutes? Probably not. But actually, yeah, so maybe I should have sped up earlier. So let me then skip this part since I'm not going to get to the, but maybe I should still point out that doing semiclassical physics, you definitely shouldn't get the page curve to work. Yet people have, by coming up with a rather simple prescription, which is this generalized entropy prescription, which has a kind of a pedigree coming from holography. Whether you like it or not, by applying that prescription, you can, in fact, for these two-dimensional black holes that we have, you can actually compute the page curve, and you get it quantitatively to work exactly the way you expect it to. So this was done in work with Vatse and Friedrich Goethersson and Lukas Schneidebauer a few years back. Basically, when very shortly after these papers, we realized that you could do this computation in the RST model, and just this simple prescription gives you exactly what you would expect, which is certainly unexpected. And I don't think we have any very, this is a reflection of an underlying unitarity, but we don't really have a good understanding of how that's being implemented. All right. So our main, of course, contribution in this paper was to assert this notion of black hole complementarity, which says that if you're an infalling observer falling into a black hole, equivalence principle holds, and you don't see anything very bad happening as you go through the horizon. If the black hole is large enough, of course, it's a bad idea still to go in because you will fall into the singularity eventually. Yet, at the same time, we claim that you can have a unitary description that would basically, if you're distant observers, you're making observations, you have your ensemble of identically prepared black holes, then you can learn the original state from the Hawking radiation coming out. Now, this sounds, of course, absolutely, and at the time it was not universally well received. And it, of course, what it requires is the information being in two places. It has to be going out in the infinite, but it also has to be allowed to go into the black hole. And the firewall, of course, would resolve this by saying, okay, you can get your information back out in the Hawking radiation, but then you're not allowed to go into the black hole. And that's what locality will always tell you. So we claim that this could still be true, and that if you really started to analyze these, when you try to push on this and see cases where you might see contradictions to this notion that you could take your that you could have your lunch and eat it. These are a very different reference frame, and we claimed that in fact they were such that in any that there was always this hidden assumption that there was some Planck scale or higher physics that came into the argument that wasn't obvious when you set it up. And a good way to see this is to go back to this experiment here. It's the same experiment, and we think about what's actually needed to make it work. Well, the point is that Bob, he has to wait before he can extract information. And if it's a black hole that has just formed, according to Page, and this was to do with the Page curve, the information doesn't start coming out until you've emitted at least half the photons that are going to come out of the black hole. So the entropy has to be reduced to a downback. And then that is what's called the Page time, and it's parametrically equal to the lifetime of the black hole. It's some finite fraction of the lifetime of the black hole. Now, this was refined by Hayden and Preskill, where you imagined you had a black hole that was past its Page time. It had been carefully monitored. And then it turns out that if you throw in additional information into it, you can, in a clever way, you can extract that in a much shorter time, but never shorter than what's called the scrambling time, which is basically m log m for a Schwarzschild black hole. Okay, so this means that Bob has to wait for quite a while, then dive into the black hole. But then the geometry is such that Alice, basically once Alice is 1 Planck length out here, inside here, her future light cone will not intersect Bob if he has waited more than a scrambling time. Okay, so what this means is that Alice, remember, she was instructed to measure the spin, transmit. This has to happen within a Planck. In the Hayden-Preskill protocol, it has to happen within a Planck time. So this means that the message and the physics she's using to do this is Planck scale physics, even though maybe that wasn't obvious from the way I posed the. So in order to be able to establish this contradiction with, or basically to learn what Charlie was up to in an acausal way, they had to employ trans-Planckian physics. And in fact, if Alice goes into a recently formed black hole, it's an exponentially trans-Planckian, e to the m. And of course, there's no way she could do that. That would require more energy than the mass of the black hole, of course. Okay. So, of course, we didn't have and still don't have a very clear notion of or a specific dynamical model to implement this. But we went sort of to the astrophysicists, and they had this notion of a stretched horizon. Which is a useful concept when you're doing, for example, numerical relativity. I don't know if they still use it, but back then computers were not as powerful as they were now. So they said, basically, if you're thinking about the interactions of a black hole with something in its environment, could be another black hole, could be an accretion ring, then you can, for all intents and purposes, replace the black hole by this membrane that's near the time-like membrane, near the black hole. By near, you mean it just has to be near compared to the distance scales that you're working with in your problem. And then you'll get a description which is kind of numerically cheaper than having to describe the full geometry and solve the Einstein equations for the whole system. So this, but they were also saying, well, this is a useful concept if you're doing interactions with things that are reasonably far away. If you're falling into the black hole, this membrane isn't there. And we just wanted to take this a little bit further. So we said, okay, we're going to define what we would call a quantum mechanical or a fundamental stretched horizon, whose property is that it is basically 1 Planck area, Planck unit. The area of it is bigger than that of the event horizon by 1 Planck unit. And that there is some microphysics associated with it, perhaps a set of, a number of qubits is a simple model. Usually the best models we have for this is some qubits that are interacting all to all, but in a k-local fashion, so only a finite number of them will interact with each other in any given interaction. And this is then supposed to, in some way, give you, first of all, you can then coarse grain this description, and that should give you back the classical membrane paradigm. You should see that physics arising, because that stretched horizon had some microscopic properties that you might be able to derive from this microscopic description. But you should also be able to basically answer any questions about the experiences of infalling observers, and all in terms of the quantum mechanical evolution of this finite number of degrees of freedom. Okay. And we followed this up with a sort of analyzing a few experiments, sort of varying degree of difficulty to carry out. Probably none of them were practical, but in all cases that we could think of, it was always true that you had made some assumption about high energy physics when you were testing this, when you thought you could do low energy effective theory to prove this wrong. So basically, we didn't really prove information return. We basically said that it's going to be very hard for anybody to prove us wrong about this. And but it allowed for the possibility that you could actually preserve unitarity. And so yeah, some
violation.
absolutely, it does, absolutely.
What extent is impact?
Sure, that's the question. Absolutely. So and let's not sugarcoat it. I mean, this is a large scale violation of Lorentz symmetry. Usually when you formulate, you know, local field theory and gravitational physics, the notion of a local event, that's the central, you know, you can disagree about, you know, relative timing and location of different events, but the notion of a local event. And there's a very important event in our lives, which is, well, I'd say there are two. The most important events is when it begins and when it ends. And what we're saying here is that the end of Alice's and Bob's life, well, they would believe, if they're infalling observers, that it happens when they hit the singularity. Charlie would conclude that they were actually absorbed into the stretched horizon and thermalized and re-emitted as Hawking radiation. And since you can have arbitrary large black holes, this is basically arbitrarily separated events. So clearly, local event will no longer be the. Now, of course, you will then the onus is on us then to figure out why doesn't this completely, you know, how do you actually get the decoupling that we see today? I mean, local events are very useful for our everyday physics. And that hasn't been answered yet, but the -2 minutes now was, so what I will do, instead of going through it, I will simply, you see this, I know this always happens. That's why I always end with the summary slide. I start with the summary slide, sorry. So there is a story that we have for how this could all work in holography. And it's recent work that we did, so that's why I think I like the story very much still. Maybe I like it less after it's been, holes are poked in it, I don't know. And so we want to use ADS-CFT because there we expect to be able to do, have unitary evolution kind of by construction, at least on the CFT side. All right. Now, describing black holes in ADS-CFT, of course, a lot of people have worked on that, but most of them have been focusing on describing the large ADS black holes and getting through the horizon to get at them. So we have a very different approach here. The large ADS black holes don't evaporate. So for the information problem, we anyway want to think about black holes that you can form and evaporate. So we do that by looking at the so-called small ADS black holes. So these are just black holes with a Schwarzschild radius that's small compared to the ADS length scale. And these are more or less ordinary black holes then that happen to be in a cosmological background that has negative curvature. Okay, so that's, now of course these are not easy to describe as, you know, because a small black hole is not a stable object, it's going to evaporate. But we're going to use that to our advantage. First of all, we need to figure out how do you map those small black hole states into the, how do you describe them in the dual field theory? Well, we don't try to describe the actual black hole. We describe the states that go on to form the black hole. And that's anyway the states that you want to have as your initial states to compare to some final state in the, but remember I told you that most of the states that can form a black hole, they're not ordinary collapsing stars or, you know, falling shells. They're in fact, and maybe this shouldn't be a surprise to us, as this is what Mukhanov pointed out, is that in order to count them, you should think about if you count the possible ways a black hole will evaporate. It sends out a stream of photons, basically of order m squared Hawking particles will go out over a time of order m cubed, each one of them with an energy of roughly 1 over m. Sure, towards the end, the mass has changed and things will happen more quickly. And so this kind of train of low energy radiation is the typical final state of a black hole. And the time reverse of that is the typical initial state. This is what we will call, as we refer to as Mukhanov states. And the nice thing is that we know how to do bulk reconstruction when there is no black hole around. We're just doing ADS with particles that are widely separated. We can describe each of those Hawking particles, with a quasi-local bulk operator, then use the Hamilton-Kabat-Lifshitz low construction to map that onto some smeared distribution on the boundary. And then we simply add them up, and we will have some rather complicated state on the boundary, very non-local, but it's still about, it's a state, it's a superposition of states in that. And these states are not energy eigenstates. In fact, energy eigenstates are probably very hard to describe here at that energy level for these small black holes. But the point here is that these are not energy eigenstates. These are states that have a width that's given by the inverse of the black hole lifetime. So they're very narrow. You should think, and this goes back to Tuft's old work. He said we should think about a black hole formation and evaporation as a resonance, as a scattering resonance. And then we have this black hole states that have width extremely narrow. They're 1 over m cubed. But the density of states is much higher. So if the dynamics that's going on here is chaotic, we expect level repulsion. And there are indications that the dynamics is chaotic. Black holes are fast scramblers. We are also but one should be able to just think about the n-body problem of these propagating Mukhanov particles, or these propagating Hawking particles, and simply see, are they described by a chaotic interactions? And David Lowe and I that's sort of ongoing work that we're trying to establish. It amounts to kind of a post-ADS analog of doing the post-Newtonian analysis of scattering in GR. But let's just take as a given that these are chaotic interactions. Then we can use eigenstate thermalization. And basically, eigenstate thermalization will explain how an initial state that doesn't look particularly thermal will actually evolve into a thermal state over so that means we take these atypical things like collapsing stars, they're going to turn themselves into a black hole rather quickly, which is then practically a thermal state. But then we basically use the formalism from Srednicki to try to estimate the corrections that you would expect to see for, so the semiclassical approximation in this picture will come from when you're calculating expectation values of observables in eigenstate thermalization, there will be a contribution from the diagonal matrix elements. You're working on the basis of energy eigenstates. Will be diagonal elements and off diagonal, and sort of the microstate dependence is all in the off diagonal, and they are highly suppressed. Now, of course, I'm just saying these words here, but this is actually what you find when you go through the. And so the picture that's emerging then is that we have these states, these resonances, which are the black holes that we want to describe. We can map the initial state onto the field theory. It will evolve in a perfectly unitary fashion there. Now, of course, during that evolution, the boundary theory is describing a configuration which has a black hole with a singularity, not a nice semi-classical description of that whole thing, but it's perfectly nice state in the field theory. Then it'll evolve eventually to an out state, which will be outgoing radiation. So in this sense, the boundary theory is resolving the singularity of the. But the things that you have to ask are precisely what Roberto was asking. How big are the deviations from semiclassical predictions that this boundary theory will predict? And we're claiming that if you're doing local observations outside a black hole, they're tiny. If you have a typical black hole state. Of course, you can construct a weird black hole state where kind of we get large corrections, but well, what we use is this expression. This is Rudnicki's expression. So a typical so what you find is you have a random matrix is a good model for, and then what typical black holes are basically sitting at the top of the Wigner semicircle. And the weird ones where you get large corrections are from the edges of that, but that's an extremely unlikely state to hit on. Okay, so that's what I mean by a typical black hole state. And then to answer your question, you can, if you want to think about an infalling laboratory, you would construct a Hamiltonian for that while it's still outside, and then you can push that forward using the semiclassical evolution here, and you can ask, how long does it? And our expectation is that that's going to give you a fairly good description of what's going on until you get close to the singularity. And then you will find, of course, the inhabitants of the lab would say the curvature is getting strong and that physics is breaking down on us. But from this point of view, it would be that there are strong corrections coming from the dual description. I have some ideas about that, not from this directly, but from doing a simple. So basically, this story that we push here is consistent with this infalling lattice model of Corley and Jacobson. And we analyzed that model some years ago. So Corley and Jacobson were interested in the radiation coming out. So we analyzed the kind of WKB evolution inside the black hole. And we found that basically you had a scrambling time. Within a scrambling time of falling into the black hole, you would hit the singularity. And a corollary of that was anything that went in more than a scrambling time before you cannot affect you in any way. Okay? And then we tried to do numerics by, modeling the stretched horizon with a bunch of qubits with non-local interactions. Now, obviously, n was, I think 14 qubits is not a very large black hole, but that's what we could do. And it was consistent being that actually the semiclassical evolution was, again, it was the same time scale. But of course, picking out a log time scale in small, I'm not going to make any strong claims based on that, but it was consistent with it. Anyway, I'm over time, and this was probably not very clear, this last part, but I just wanted to give you a notion that there are ways that this could all work. And thank you for your patience. Questions?
Can you comment about the paper by Donald Mao in 2015? Proposed that
Okay. I'm not familiar with it, so let me refrain. But thanks. I will take a look at it. But if that was a stationary state, then it's probably not going to be. Then that's more like trying to come up with one of these energy eigenstates. But I'll take a look at that. Thanks.
very long.
Yes. Right. So, yeah, look, I should emphasize that these energy eigenstates that I'm, doing my expansion on, those are probably non-geometric even. They are not, don't have any nice geometric, and they don't need to have that. Which is of course very different from the large ADS black holes, where you have this thermal field double when you can actually have a very simple geometric description.
Geometric microscopes. Whether we believe that, No. What's the price for more like
Okay.
there are, I mean, in that case, there are geometric. Doing something something that's happening.
I guess one reason we were happy with this story of ours was that we didn't need to know what they were. We simply make the assumption that due to the chaotic interactions, we have level repulsion. That tells us that we will have an enormously dense density of states. And it, you can basically take it from there. You don't. Okay. Now that would of course be, I mean, this is a major assumption that we make. But that's you can't use. Sure. Sure. And in fact, many of these initial states will probably not form black holes, but something more short-lived. That's true. Those will be, even broader resonances. The thing that, well, yeah, the lifetime, the width of the resonance will. Now, of course, there's something that is missing from here, which is the details of what is actually, my expectation is that once I derive, from the diagonal matrix, is that ETH will give me GR plus matter fields, in which case I know that generically it's falling in will form black holes. Now, of course, I haven't derived this, but it's, since the dual of the field theory is ADS gravity, I think it's a reasonable expectation.
Perfect or somehow even like the meaning of the right.
Well, the thing is that the dual description kind of can do its thing without, if you ask what is the state at a time where you know that you have a black hole there, it's not really going to describe, the part that would describe the singularity is where the kind of the semiclassical approximation is breaking down and have these corrections to it. So I don't think this will, it resolves the singularity in principle, but it doesn't really give you a geometric picture, at least not immediately. Well, I think sort of the point of this exercise was to avoid having to do that. I mean, we have an initial state, we can evolve it to a final state. If I try to do that using the semiclassical physics, of course, I will fail miserably. If I start with some initial state and I want to compute, let's say, a transition amplitude, take an observation on early and late times. So there are two ways you might do that in the boundary theory. You would take an initial state, you would evolve it forward and calculate an expectation value of that final, or you could do it the other way and go the because it's a unitary theory. If you do the semiclassical evolution forward, you would form a black hole, you would get some radiation out. If you try doing it in the other opposite, you will probably get order 1 errors. So that really, those kind of observations, so transition amplitudes, the semiclassical description breaks down completely, but that's what you expect. That is the information problem.